Hello, my dear future doctors. This video presented by Dr. Luqman's Medical Academy is about organic chemistry. It is an organic chemistry marathon, and hopefully, this video will make you become the master of organic chemistry. These are final revision series videos. These are not explanatory videos. These are the revision videos. If you study these videos properly, if you watch these videos on a regular basis and multiple times, I can guarantee you that nearly 70 marks can be easily scored in the NEET examination. So these are marathon organic chemistry. Most students are always worried about organic chemistry. They fear that organic chemistry is hard to understand, that the structures, the isomerisms, the IUPAC names, the coding and the numbering of the carbon atoms, and all those things are very hard to understand. Most students make it very like they ignore this one, but I can assure you that just you watch these videos and you hope you will be perfect in the organic chemistry. These are the revision videos. Actually, I'm not going to explain every topic in detail, but I'm going to touch the every topic directly as an exam oriented notes with the previous year integration. What you will master here is you are going to get strong conceptual foundations. You're going to see some high yield theory with visuals, and you are going to see some neat previous year questions integrated within that topic, and examiners tricks and smart tips also you will be finding here. All these video series are from the NCERT basis. All are exam focused. Concept clarity, practice and perfection, your success is our goal. Organic chemistry for NEET. Organic chemistry accounts for roughly 35% to 36% of the NEET chemistry section. One of the largest section of the NEET examinations are expected from the organic chemistry, and that means nearly 14 to 16 questions, sometimes 17 and 18 questions have been also asked. That accounts for more than 70 marks or 64 or 68 marks. Sometimes it depends upon from year to year, and these questions are expected from this NEET organic chemistry chapter. So in this video, we are going to study all those topics which are going to make you perfect in these 14 to 16 or sometime 18 questions. We are going to study directly from the NCERT. This video will make you NCERT master. Direct NCERT lines are asked in NEET, NCERT examples and tables, reactions and exceptions. We are going to study each and everything, and we are going to integrate with the previous year question, and so that once the 16 questions of the organic chemistry are on your paper, you're going to confirmly do the right answer. Moving on, I would like you all to subscribe my YouTube channel, like the video and comment. You can comment about what are your needs and requirements, or you can also comment if you have any doubt in this video of my explanation. I will definitely reply to you, and also do share to your friends. Help me help other students. Let's see first of all organic chemistry. This is the basis of organic chemistry. You are going to understand the organic chemistry only when you are going to understand the carbon and the carbon atom hybridization. Hybridization. First of all, let's also cover some of the basics. Hybridization means mixing of the s and p orbitals. We know that every atom has shells and orbitals. We have orbital angular momentum and magnetic momentum of that orbital. So there are, we name that one like SPDF. So in the s and p orbitals of similar energy to form a new set of equivalent hybrid orbitals. So two orbitals of same energy are going to get mixed, and they are going to form the same energy level, equivalent energy hybrid orbitals. That type of intermixing and formation of new equivalent hybrid orbitals is called as hybridization. So the important topic you have to study is carbon. This carbon's nature of tetravalency and the nature of hybridization, That is the reason why this organic chemistry is so vast, and there are many reactions, many concepts, many theories, and the whole organic chemistry is a new world. The whole new world has opened just because of the special behavior of the carbon atom, that is tetravalency and hybridization. Carbon has four valence electrons. It is called as tetravalent and forms four covalent bonds. Okay, let's see first of all hybridization. This table actually is given in the NCERT, and direct table based statement based questions can also come here. Okay, in the hybridization of sp3 hybridization, sp2 and sp hybridization, the s character and the p character and the angle and the geometry. It means after hybridization, how much of the s character is present in that hybrid orbital, how much of the p character is present in that hybrid orbital, and what is the bond angle in that hybridization, and how does it look like. 3D model of that orbital and that hybridization is shown, and we are going to study that one. It is very important. S character in the sp3 hybridization is 25%, and sp2 hybridization it is 33.3%, and sp is it is 50% s character. And in the same way, p character in the sp3 hybridization is 75%, and in the sp2 hybridization the p character is 66.7%, and in the sp it is 50% character. Okay, so bond angle in the sp3 hybridization is 109.5 degrees, and in the sp2 hybridization the bond angle is 120 degrees, and in the sp hybridization the bond angle is 180 degrees. So after studying this bond angle, what you have to remember is geometry. Okay, these questions are commonly asked even in the previous chapters also. I mean to say in the in the inorganic chemistry also these questions are coming about the hybridization. So the tetrahedral geometry in the sp3 hybridization, and there is a trigonal and planar type of geometry seen in the sp2 hybridization, and there is a linear hybridization and the geometry in the sp hybridization. A number of hybrid orbitals are 4 in sp3 hybridization, and 3 in sp2 hybridization, and 2 in the sp hybridization. Unhybridized p orbitals are 0 in sp3, 1 in sp2, and 2 in sp hybridization. Example are ch4, ch3cl, c2h4 when it comes to sp2 hybridization, and ch2o. And also when it comes to sp hybridization it is c2h2 and chn. So these are the direct table based questions you can get from here, and the percentage of the s character increases from the sp3 hybridization to sp hybridization, and the percentage of the p character will is decreasing from the sp3 hybridization to s hybridization. You can see the diagram here, sp3 hybridization. You can see the orbital mixing also, and how the orbital mixing is going to happen to give you these four equivalent sp3 orbitals. So number of hybrid orbitals are 4, you can see here, and the angle is 109 degree 5 minutes. So these all diagrams will give you a clear picture, and after seeing and after having these visuals in your brain now, it will be easy for you to understand and also remember. So stop the video here and study. Okay, let's first of all understand why, like why is behind every concept. Okay, why s character matters. The greater the s character, orbitals come closer to nucleus, and bond length decreases, bond strength increases, and electronegativity of the carbon increases. So in the sp orbital there is s character highest. It means in the sp hybridization the s character is highest, it is 50%. So if the highest percentage of the s character is present, then the orbitals are coming closer to the nucleus, and that's how the bond length decreases and bond strength increases and the electronegativity of the carbon increases. So when it comes to the strength of the bond, obviously sp hybridization is more stronger than the sp2 hybridization, and it is stronger than the sp3 hybridization. So you have to remember the why behind the hybridizations. The take home message is carbon is tetravalent and forms 4 covalent bonds. Hybridization explains shape, bond angle, and reactivity, and greater the s character, shorter stronger bonds, more electronegative carbon is present. Okay, so remember that then sp3 less than sp2 less than sp when it comes to the stronger bonds. Now comes the sigma and pi bonds. Even though we study the sigma and pi bonds in the chemical bonding chapter, but here also it is very important because these bonds are making carbon very special, and that is the reason we are going to study all about the carbon in the organic chemistry. Let's study first of all what is sigma bond. These are the basics which we also cover in the chemical bonding chapter in organic chemistry. Okay. Sigma bonds are formed by end-to-end overlap of the orbitals. So we know that every atom, every element has orbitals, that's sp_df. If the ss orbital and sp orbital and pp orbitals are overlapping end to end, okay, then that type of bond is called as sigma bond, end to end orbital, okay, bonding overlap. Electron density lies along the internuclear axis. So because they are overlapping end to end, the density of the electron to be found lies along the internuclear axis. You can see the axis here. Okay, this is the internuclear axis, internuclear axis. Okay, so this free rotation is possible because it is end to end overlap. Then the rotation is freely possible. Now let's see what do you mean by pi bond. Pi bonds are formed by sidewise overlap of the unhybridized p orbitals. So this is very, very important. You can see there is a sidewise overlap of the unhybridized p orbitals, and electron density lies above and below the internuclear axis. This is the internuclear axis. The density of finding the electron is above the internuclear axis and below the internuclear axis, and there is no free rotation, weaker than the sigma bond but more reactive. So sigma bond is stronger and pi bond is weaker. Sigma bond is less reactive, pi bond is more reactive, and free rotation is possible in the sigma bond, free rotation is not possible in the pi bond. Electron density lies above and below the internuclear axis in the pi bond, and electron density lies along the internuclear axis of the sigma bond. So pi bonds are weaker but more reactive than the sigma bond. This is one small gist about what are the sigma bonds and pi bonds. Okay, so number of sigma bonds and pi bonds and lone pair electrons in the pyridine. In the previous slide, there could be some audio disturbance. I just want you to stop the previous slide and study all the sigma bonds and pi bonds are forming, and that type of questions have been asked in the previous year NEET examination also. Let's study the structural representations. Okay, this is very important. These are very basics also. If you are very clear about these, then only we can understand different type of reactions, different type of scientist reactions, preparations, and all other chemical parts of the larger organic compounds if you are perfect in the structural representations. So let's see what do you mean by structural different representation. It means how do you represent a molecule. There is a molecule, there is like CH3, CH2, CH3, then that molecule has to be presented. It is a butane. So how do you present the butane in a structural form? And there are different ways of presenting that butane chemical molecule, and that is called as structural representation. Let's see what are they. Complete structural formula shows every atom and every bond. You can see there are four atoms, the bond between these two carbon, and these two carbon, the bond between the CH and CH and CH, all the atoms and all the bonds are shown. This type of representation is called as complete structural formula. Now comes the condensed structural formula, groups atoms together. So H3, all the H at one place, then H2, H2, H3, and you also group in the brackets, shows the connectivity but not all bonds. So it will show what is the connectivity in that molecule, but it does not show all the bonds. Okay, these questions, the questions will not come in this format, but you have to understand this representation in order to understand the other slides very well. Bond line. So each vertex and line end represents a carbon, and hydrogens are not shown, heteroatoms are shown. This type of is called as bond line skeletal formula. So these are very basics, and these are very like volatile topic. One should not ask the questions from here, but if the questions can come, obviously it will come in a statement format. Okay, example, like for example, 3-methyl octane. You have to understand that there is a octane first, like there are 8, 1, 2, 3, 4, 5, 6, 7, and 8 carbon, therefore octane. And at the third carbon, there is 1 methyl. So that is 3-methyl octane. How do you represent the 3-methyl octane in the structural formula? How do you present the 3-methyl octane in the condensed structural formula? You can see after third carbon, you are adding the CH3 in a written format. Okay, and how do you represent the bond line, that is skeletal formula? If you, for example, by this you have to understand, if there are these zigzag lines, then this is one carbon, this is one carbon, this is one carbon. You have to understand all these carbons, you have to count, and you have to name at what carbon which element is been seen, and that's how you will identify the name. By seeing even this linear bond line skeletal formula also, you can name the that organic chemical compound. So that is why these structural representations are important. Why does it matters in NEET? Questions in NEET are based on identification. Any question you have to answer when it comes to organic chemistry, first of all you have to identify that molecule, you have to name that molecule. Then once you identify and once you name the molecule, then only according to the arrangement you will name, and according to the naming and arrangement you are going to find out isomerism and reaction understanding. So quick conversion between the representation is essential. Let's remember the key points. In bond line formula, each vertex is carbon atom, each line end is carbon unless a hetero atom is present. It means this type of lining, okay, this skeletal lining, zigzag linings, each line end carbon unless a hetero atom is present. Hydrogens on carbon are implied but not shown. Hetero atoms, that is oxygen, nitrogen, sulfur, and xenon, etc., are always shown. So let's see what is the explanation. Bond line formula is also called a skeletal formula. It simplifies complex molecules by showing only the carbon skeleton and functional groups. This makes it easy to visualize large organic molecules. The trick here is always count carbons from the skeleton, vertices plus line ends, and then add hydrogens according to the valence, that is C is equals to 4. Okay, so the type of formula, what is shown and what is the advantages of these skeletal representation is shown in here. Okay, so the revision is a complete structural formula shows everything, condensed shows only groups atoms, bond line only shows carbon skeleton only, other has to be understood, and each end or the vertex is carbon. Most NEET questions use bond line formulas. Practice converting between the three representations quickly. So in the question there are directly like bond line questions are coming, so you have to understand this bond line, then you will understand that chemical compound, and then you are going to answer the question which is present in that question. Okay, now comes the 3D representation. Okay, that 3D representation happens through wedge dash method. Visualizing the molecules in 3 dimensions is called as 3D representation, that is done by wedge dash. What is happening here? What is wedge dash representation? It is a way to represent 3D structure of a molecules on a 2D plane. It means on a white paper. So if there is a solid wedge, then bond coming out of the plane towards the observer. If there is a wedge like, then it is that is above the plane. It is having a 3 dimensional. Okay, but we are showing it on the 2D plane like a paper. If there is a dashed wedge, then bond going behind the plane away from the observer. So it is going behind the plane away from you. Okay, so if there is a wedge, then it is towards you, and if there is a dashed wedge, then it is away from you, and if it is a straight line, normal line, then it is on the plane, it is plainly present on the paper of that line only. So you have to remember this one. Direct questions are not coming from this side, but if somebody, if the examiner give this type of question, then he asks about the plane, and also if ask about the angles, then you have to identify by understanding this wedge dash structural representation of the 3D structure of the molecules. Why more S character gives stronger CH bond? Because obviously the more S character means it is more closer to the nucleus, stronger attraction between the CH and H nuclei, more energy is required to break the bond. That is why they are more strong and more stable, and there is a high bond dissociation energy is required. Okay, so these are some of the NEET previous year questions. Bond dissociation energy order of the CH is different. Hybridization, more the S character, there is, it requires more dissociation energy, therefore SP has more S character compared to sp2, and sp2 has more S character compared to sp3, and the detailed explanation is also given here, which we have already studied in our previous slides also. You better just stop the video and understand and study properly. The CH bond length also has been given. The CH bond length in the sp hybridization is 106, and sp3 is 109, and sp2 is 109, and sp3 is 113, and the bond strength is highest in the sp and intermediate in sp2 and lowest in the sp3, and that is what you have to remember. The reason is more is the S character, stronger is the bond. So if the stronger is the bond, then it requires higher bond dissociation energy. This is very important slide when it comes to organic chemistry. All you have to like identify the molecule, name the molecule, identify the circles, and how does the you name it, what are the functional groups it is presenting, and what is the prefix, what is the suffix, and how are you going to identify the principal functional group, and all these things are present in this slide. This is very important. There are many questions which are, then there are very topics which we are going to study in the next video, in which there are a lot of molecules. For you to understand that molecule and chemical reaction, you should first of all know about the classification of the organic compound. You should know about the functional groups, principal functional groups, how to name those groups, and how do you attach the suffix and prefix. All these rules are very important. Let's see the broader classification of the organic compounds. Organic compounds can be classified as acyclic and cyclic. It means those compounds which are not circular, okay, which are not arranged circular, and those compounds which are arranged circular are called as cyclic or closed chain. Okay, it has another name also. The acyclic organic compounds are called as aliphatic, and those which are cyclic are called as closed chain. Now, when it comes to the acyclic, again we have one type that is called as straight chain. It means there is complete one straight, there is no branch, and another it is having a branched chain. And when it comes to cyclic, we have alicyclic. It means non-aromatic acyclic, and we have aromatic, that is planar and conjugated. Again, in the aromatic type also we have benzoid, example benzene, that is it is having that hexagonal shape, and non-benzoid or heterocyclic aromatic, that is pyridine and furan and thiophene. So we are going to study each of these molecule again in detail. As of now, we are only trying to understand the classification of the organic compounds and main categories. So you have to remember these categories and what does do they mean. When coming to each and every compound, we are going to study in the further chapters. So these are the examples when it comes to organic compounds. Let's see about the functional groups. Okay, so these are the classes of the organic compounds, and these class has these functional group, and the functional group chemical formula and the structure is this one, and it has the suffix according to the IPAC as ol, and it has some prefix also. Let's see one by one. Okay, so for alcohol group of organic compounds, the functional group is hydroxyl. The structure has OH ion molecule, and suffix according to the IPAC has to be added as ol, and the prefix to be hydroxy. And aldehyde class group has formyl functional group. It has structure of OCH and suffix added as al, like, and the prefix as a formyl or oxo. And the ketone group has keto functional group. Keto means OC only, O double bond C, and the the suffix usually is on, like ketone, and the prefix is oxo again. So oxo can be used for aldehyde and ketone when it comes to prefix. You have to remember this one. And carboxylic acid, carboxyl has the functional group structure OCOH, and the suffix is oic acid, and the prefix is carboxy. Okay, alcohol has the prefix as hydroxy, and the carboxylic acid has the prefix as carboxy. And the amine, in which the functional group is amino, and the structure is NH2, suffix is amine, and the prefix is amino. Nitrile, the functional group is cyano, that is C triple dash N, and the suffix is nitrile, and the prefix is cyano. And the same way for the class halide type of organic compounds, we have the functional group halo, that is any of the halogen, that is chlorine, bromine, and iodine. And there is no suffix for these type of functional groups, but the prefix added for the halide things are halo. So you have to remember this table. You have to by heart each code, like class of the organic compound, the functional group present in that class, and the structure and the suffix and the prefix, so that it will help you in the naming. Obviously this will become perfect only through practice. Now very important thing is priority order for principal functional group, from high order to the lower order. This rule itself is very important in the IUPAC nomenclature also, and also among the a lot of reactions. So let's see. Obviously, according to the priority, carboxylic acid has a higher priority compared to sulfonic acid. Then comes the ester, more than the acyl chloride, more than the amide, more than nitrile, more than aldehyde, and more than ketone, more than alcohol, more than amine, more than alkyne, more than alkene, and more than halo. It means the lowest priority order is halogen, and the highest priority order is carboxylic. You have to by heart this what you call as functional group priority, but obviously it is sometimes hard to by heart. So we have a mnemonic here. It is a like a technique to remember actually. Carboxylic students studying can't cheat on exam giving papers, or teachers always answer correctly. So this is the mnemonic you have to remember, that carboxylic students studying can't cheat on exam giving papers, or teachers always answer correctly. So carboxylic for carboxylic acid, students for sulfonic acid, studying for ester, and can't for acyl chloride. And in the same way we have all these names which starts with either the letter C or A, and that's how you arrange all these one. So this example of mnemonic is somewhat helpful. If not, you have to directly by heart. Better you by heart direct this order, because by that you also remember the name and also the functional group present in that name, and that will be easier during the chemical formulations and IUPAC name and the chemical reactions. The rule is choose the highest priority group as a principal functional group, give suffix and parent chain, and other groups are treated as substituents, or give the prefix. Suppose in a chemical formula there are two groups. There is a carboxyl group also, and there is a ketone groups also. So you are going to choose carboxylic because it has having high priority, and you will name the suffix and parent chain with the carboxylic only. And if it has ketone also, then you will give the prefix as a ketone name. So that's how you study. Or if there is only one, obviously you are going to go with only one. So this is the order. NEET previous year question, you can see the IPAC name of the compound given below is. So you have to understand the IPAC name. Okay, so 5-oxohexanoic acid. First of all, hexa, you have to study 1, 2, 3, 4, 5, 6, 6 carbon. So it is hexa. Okay. Oic acid, oic with comes always with the carboxyl acid or carboxyl functional group, and carboxyl functional group is present with COOH. So COOH is present, so therefore it is carboxyl. So at the end there will be oic. In the suffix also it will be oic. So you have to understand this one. Okay, stop the video here and try to solve this properly, and it will be helpful for you. The quick facts are cyclic compounds are more stable due to ring structure, and aromatic compounds follow Huckel's rule, that is 4n plus 2 pi electrons. We are going to study the Huckel's group and Huckel's rule in our further slide. As of now, just remember as a quick fact, but we are going to study in the next slides. Functional group decides the chemical properties also. Always choose the parent chain ring containing the principal functional group. So those compounds which are cyclic, okay, these are more stable due to the ring structure. These are more stable when compared to the acyclic ones. Okay, moving on. IPAC nomenclature. This is very important, but it has to be explained on paper in detail. As of now, I am giving you exam focused rules. Okay, NEET focus is always alphabet decide order and number decide order. Always he is going. He knows that you can name like it, myth, and prop, butane. This he knows you, but he is going to confuse you at the alphabet order and also the number decide order also. So let's see the rules first of all. Rules to name the branched alkanes. So longest carbon chain, choose the longest continuous chain parent alkane. Then there is a numbering, then give numbering from the end, which gives the lowest set of locants positions to substituents. And the alphabetical order, arrange different substituents in alphabetical order, ignore di, tri and tetra etc. Compare only the root names. Same substituent, use di, tri, tetra. If the substituent is same, then only you use the di, tri, tetra etc. and separate numbers by commas. Hyphen between the number and name, commas between the numbers. So these are the rules you have to remember. So longest carbon chain, numbering has to be given at the from the end of the lowest set of locants positions of the substituents. Alphabetical order you have to give, but ignore di, tri, tetra. If the substituent is same, then only use the di, tri, tetra and separate the numbers by commas and the hyphen. Let's see an example how to name. So this is a compound. Obviously you have to count the number of carbons. 1 2 3, there are 7 carbons, therefore it will be heptane. Longest chain is 7 carbons, so heptane. Numbering from the left gives locants at the 4 ethyl and 3 methyl. From right would be 4 methyl, 5 ethyl. It is the highest set. So alphabetical order, ethyl E before methyl M, so name should be 4 ethyl 3 methyl heptane. So this is the name. So according to the alphabetical order, you have to take E, because in alphabet it E comes first and then comes the methyl. Okay, but giving the numbering, obviously numbering you have to start from the end which has the lowest set of the what you call as substituents. Okay, so according to that one you will number 4 to the ethyl, and you will give 3 to the methyl. Moving on, NEET common error which has been also asked in the previous year question is correct name is 4 ethyl 3 methyl heptane, but wrong is 3 ethyl 4 methyl. Why alphabetical order? Because ethyl comes before the methyl. It is in the alphabets, E comes before the M. More examples to practice. You can see here 2 methyl propane isobutane, 2,4 dimethyl pentane, and 2,2 dimethyl butane, 3,5 dimethyl octane. So stop the video here and practice in detail. You have to pen down actually, and that then only you are going to remember. If not, by just watching it will look easier, but in the examination it is going to consume your time a lot actually. Lowest set of locants means you have to observe that 2,4 dimethyl pentane, in which you can see 2 and this is 4 lowest set of locants. Okay, but it is not like 2,4 dimethyl pentane higher set of locants. Okay, here you can see here, this is the difference you have to make out. Just first of all pen down, that is how you understand. Okay, alphabetical order, obviously it will be ethyl, methyl and propyl. Order is ethyl, methyl, propyl, and this should not be the one. Okay, diethyl, dimethyl, that is not the order. You should not confuse with this one. Okay, NEET high yield tips are always choose the longest chain. Lowest set of locants is must. Alphabetical order only for different substituents. Same substituents you will use di, tri and tetra. Hyphen between the number and name. Example 3 ethyl 2 comma 2 dimethyl hexane. So one line memory, longest chain, lowest numbers, alphabetical names, hyphen and commas, you are done. Now comes the alkenes and alkynes IPAC nomenclature. So suffix "ene" means double bond. Whenever you see a carbon compound, an organic compound in which the carbon has double bond, then that compound has to be named as "ene." and suffix, and if that bond is triple bond, then comes the ine. This is the basic you have to remember: double bond ene and triple bond ine. Let's see the rules for alkenes and alkynes. Choose the longest carbon chain containing the multiple bond. Number the chain to give the lowest number to the multiple bond. If both double and triple bonds are present, give the lowest number to the first multiple bond from chosen end. If tie, then double bond, that is ene, gets the preference over the triple bond ine. If more than one multiple bond of the same type, use di, tri, and give all locants. List multiple bonds in the suffix part in order of ene before ine. So these are the rules you have to remember. Okay, stop the video and read again, then see this video. For example, double bond gets lower number, hex 1 in 5 ine, also written as 1 hexene 5 ine. Okay, there is a ene also and there is a ine also. Here there is a double bond and there is a triple bond, so we'll give double bond ene first, then we'll give the triple bond ine last. Lowest number to first multiple bond, there is hex 2 n ene 4 ine. So you can see hex 2, then there is ene and there is a 4 ine. So this is the lowest number to first multiple bond. And two double bonds or two double bonds, use diene, penta 1 3 diene. There is one double bond, this one 1 and 3, so there is penta 1 3 diene. Penta means 5 carbons. And two triple bonds, use diene, like penta 1 4 diene. This is the triple bond, this is the triple bond 1 and at the 4, and that's how you name it. You can see the examples here. These rules, all the rules have applied in this example, so read the rules properly and see the example so that these rules can be understood easily. The NEET previous year question, you can see here, name the following compound. He's just, there are no other substituents, you have to name according to the double bond and triple bond. So the name is hex 1 ene and 5 ine, also written as 1 hexene 5 ine. So first multiple bond from left is at C1, double bond. If numbered from right, a triple bond would be at C1, hence double bond gets the preference. Total possible isomers or structural plus stereo of the cyclic ethers C4H8O is 10 isomers. We are going to study these isomers, types of isomers in detail again. Let's see. Cyclic ether C4H8O, all 10 possible isomers including the stereo isomers are present. Okay, three membered ring oxyranes. These one isomer is three membered ring, 2 methyl oxyrane propylene oxide. One isomer is oxytane and one isomer is 3 methyl oxytane. One isomer is tetrahydrofuran and the other two isomers 5 membered ring. Here 3 membered ring 1 and 4 membered ring 2, and the 5 membered ring also here it is present. These are 3. Okay, and there are two stereoisomers, cis 2,5 dimethyl tetrahydrofuran and trans 2,5 dimethyl tetrahydrofuran, and that's how there are total 10 isomers. Exam tips you have to remember here is always highlight the longest chain first, give the lowest number to multiple bonds. If both the double and triple bond present, double bond takes the priority in tie. Write ene before ine in the name. Quick takeaways: only double bond ene, only triple bond ine, both present, lowest number to the first multiple bond. If the ene gets preference, if there is a tie, then ene gets the preference. More than one multiple bond, use di, try with over locants. The one line memory is lowest to multiple bond, double before triple, alphabetical for substituents, di, try with numbers inside. Alkene ends with the "-ine" and alkynes ends with the suffix "-ine". I would request you all to subscribe to the Medicon Academy channel, like the video, comment in the comment section if you understand something or if you don't understand something, if you have some another thing in your mind, like if you want this topic in detail, or if something from the slides also, if you have doubt, you can comment here and share the video to your friends. Help me help students. So substituted benzene, IPAC nomenclature, the rules of ortho, meta, para and exam questions are explained here. Okay. So what do you mean by the rules of substituted benzene? For example, simple substituent, that is one type, name as prefix plus benzene. Examples: chlorobenzene, nitrobenzene, and methylbenzene. So in the benzene ring, if there are substituents like extra added chemicals of the as a head or tail to the benzene ring, such type of substituted benzenes you have to name like this. So as a, if there is a simple substituent like one type substituent, then you will use in the prefix as chlorobenzene and nitrobenzene and methylbenzene called as toluene. But if the di-substituted benzene, it means there are two, then common names use OMP to show relative positions like O for ortho 1, 2, M for meta 1, 3, and P for para 1, 4. If the positions are 1, 2, the substitutions, there are many substituents. If there are two substituents and they are in the position of 1, 2, then the name should be ortho, and if those are in the positions of 1, 3, then the name should be meta, and if the names are in the position 1, 4, then the name should be para. You have to stop the video and study that in a proper way. Moving on, let's see one of the neat question also. Correct IPAC name for the compound. There is a benzene ring. Then you have to name the substituents. Okay, you have to, how do you name like 1, 2, and 4? The answer should be 4 ethyl, 1 fluoro, and 2 nitrobenzene. So this is the answer. Okay, there are some problems also, NCERT style problems. So stop the video here and try to solve that problem. It is very easy actually. You have to just follow these rules. Here there are many more examples given. The NEET previous year question insight is that correct numbering for the lowest locants, alphabetical order of substituents, priority of the multiple bonds and functional groups over substituents, common names versus the IPAC names. So the quick tips are: identify the parent benzene ring. For di-substituted, use O1, for at the 1, 2 position use ortho, and at the 1, 3 position use meta, and at the 1, 4 position use para, and number from the substituent that gives lowest locator first. So the substituent, if it is CH3 methyl, then it counts as methyl M, and in the same way that goes in the sequence. You already know that one. Let's see what do you mean by isomerism. What, there are two types of isomerism, that is structural isomerism and stereoisomerism. Okay, so basically, the isomerism, the structural isomerism, same molecular formula, but there is a different connectivity. And because of the connectivity, also the properties of that same chemical formula containing compound will change. The properties are also affected. That is called as isomerism. Structural isomerism, it means in the structure of their bonding and function, there is a some isomerism. Okay, so chain isomerism, molecular formula C5H12. The examples are N-pentane, isopentane, and neopentane. So this is N-pentane, this is isopentane. There is one branching here. Obviously, there is a change in structure, but the compound molecular formula is same, and there is a neopentane. The whole branching is different. So for the same chemical formula, there are three different structures. That type of structures are called as isomerism. If they are, the change is the change is in chain, then it is called as chain isomerism. Position isomerism, that where is the position of the main compound we are talking here. In that sense, C3H8O, propane 1 ol or propane 2 ol, and depending upon the position also, the compound properties changes. That is called as position isomerism. And now comes the functional group isomerism, like for C3H6O, propanol, aldehyde or acetone, ketone. Okay, if the position and the functional group is changing for the same chemical formula, then those are called as functional isomerism. Then comes the metamerism, in which the methoxypropane, methyl propyl ether, ethoxy ether, and diethyl ether, these type of namings and these type of structural positioning of this molecular formula is called as metamerism. So same molecular formula, different arrangements, different properties, structural isomers differ in the connectivity of the atoms. This is about the structural isomers. Let's see about the geometrical isomerism, in which there is a cis trans or EZ type of position requires a carbon double bond, where each carbon has two different groups. Okay, so these are the previous year questions which have been asked. So which of the following shows geometrical isomerism? You have to remember, right? You have to first draw. There are each double bond carbon have two different groups. This the carbon has different group and this carbon has different group, and that is why it is called as geometrical isomerism. Optical isomerism requires a chiral carbon. What do you mean by chiral carbon? Means a carbon attached to four different groups are called as chiral carbon, and that is why they are called as optical isomerism. So malic acid, that is cis butanoic acid, does not show optical isomerism but shows geometrical isomerism. This example has been given here. In the same way, how many stereoisomers are possible for this number? So you have to understand that geometrical isomerism are 2 and optical isomers also 2, because chiral carbon at the CHBr, you can see here this carbon is chiral carbon. So total stereoisomers are 2 into 2, that is 4 stereoisomers can be possible with these presentation. So structural isomerism, different connectivity of atoms. Types are chain isomerism, position isomerism, functional group isomerism, and metamerism. Stereoisomerism, same connectivity, different 3D arrangement. Types are geometrical, optical. Optical isomerism, also called as enantiomers. The exam tips here are: check the conditions for geometrical isomerism carefully, and the chiral carbon goes into optical isomerism. One line memory is to remember: connectivity changes structural isomers, spatial arrangement changes the stereoisomers, and chiral carbon optical isomerism. So let's start with the reaction mechanism core concepts. So these are the reactions which we are going to study all along our approach. Okay, now these reactions are basics actually. If you understand these reactions, then obviously all the other organic compound reactions can be easily understood. So let's see what do you mean by like bond fission, that is cleavage. Okay, there are some concepts we are going to study. Just to focus on the slide there. Okay, for example, chemical reactions start with breaking of bonds. There are of two types: heterolytic fission and homolytic fission. And in this heterolytic fission, obviously hetero means different and homo means similar. So in the heterolytic fission, both bonding electrons go to one atom, and intermediate formed is either carbocation, that is with plus being added, or carbocation or carb anion actually. So with the negativity, it means with the loss of the electron. So heterolytic fission, in which both the bonding electrons go to one atom. So in comparison to that one, homolytic fission. In the homolytic fission, bonding electrons are shared equally, and there are free radicals found in as the intermediate, and the representation, you can see the full curved arrow from tail starts from electron pair, and whereas in the homolytic fission the representation is a half-headed arrow, fish hook arrow, one electron is being shared. So there is a free radical production here, and there are carbocation and carbanion produced during the heterolytic fission. So this you have to understand, like where the bond is doing the cleavage. Cleavage means where it is dividing. Okay, depending on that one, there are two reactions. One is heterolytic fission and the another is homolytic fission. Let's see what do you mean by these carbocation and free radical and carbanion. Okay, now stability orders of the intermediates, very high yield question this one. Okay, stability order, if it is like for example, you can see here it's a butyl. There are how many carbons? Two, three carbons. Okay, and after the reaction it has three carbons, so it is tert butyl. It means tertiary butyl. Tertiary butyl. And here we have isopropyl, secondary, and primary ethyl, then methyl. So when we compare with this one in the anion form, being a carbon organic compounds ion. So carbocation. When we see this, tertiary butyl is having more stability compared to isopropyl secondary, then compared to ethyl, then compared to methyl. When it comes to free radical, here stability is equals to hyperconjugation. Okay, what is hyperconjugation and what do you mean by these effect, alkyl group effect? We are going to study that in detail here. Okay, you don't worry. First of all, just see these increasing order and decreasing order, because direct questions are coming from this area. Okay, when it comes to free radicals are formed in homolytic fissions. Okay, whereas these carbocations are formed, or carb anions are formed during the heterolytic fission. And in the free radical also the same sequence is being followed. And when it comes to carb anion, that is alkyl groups destabilize negative charge by positive I effect. Okay, that is ionization effect. We are going to study that one in detail. So here methyl group has more, that is methyl ion. Okay, carb anion has more stability when compared to the other one. Here it is, the reverse order can be seen here. So direct question can be coming from these areas. Okay, why are these orders happening? Let's see. In the carbocation or the free radical, in both these places, they are stabilized by hyperconjugation. What do you mean by hyperconjugation? It means positive H effect stabilizes the positive charge and radicals. The positive H, the H plus, okay, this stabilizes the positive charge and radicals. And positive I effect of the alkyl group destabilizes the negative charge. This is the reason for opposite trends in carbocations versus carb anions. You can see here. The carbocation or the free radical is stabilized by hyperconjugation, delocalization of electrons from CH sigma bond to empty p orbital or radical center. More alkyl groups, more alpha hydrogens available, more hyperconjugation, more stability. So this is the reason for carbocation having more stability, and this is the reason why this tertiary butyl is more stable when compared to the methyl group or methyl carbocation. The same, but in opposite direction, there is that you have to apply carb anion. The negative charge on carbon alkyl groups are electron releasing. They push the electron density towards the negative center, that causes destabilization. Hence fewer alkyl groups, more stable carb anion. So that is the reason the order is reverse here. Okay, remember, stable intermediate favored pathway high yield product are produced. This was the previous year NEET questions also. He has given increasing stability of carbocations. So obviously in carbocation, increasing means obviously you have to start from methyl group. Okay, because from lesser to it has to be higher. Here we have given the order from higher to lesser. Okay, break the bond, form intermediate. Stability decides the pathway. Carbocation and radical, tertiary is more than secondary, is more than primary, more than the methyl ion. And for the carb anion, obviously the methyl is more than the primary, more than the secondary, and more than the third tertiary. And more stable intermediate produces higher yield. So this was about the reaction, the main concepts being like heterolytic fission or homolytic fission. Moving on, nucleophiles and electrophiles. Phile or phily means like. Like if I like an electron, then I am electrophile. If I like the nucleus but not the electron, then I am nucleophile. So phily means liking. If I like something, then that word with an adjective is attached to me and being called as phile. That is called as phily. So nucleophiles donate electron pair, whereas electrophiles accept electron pair. So electron pair being accepted, it means electron is being liked, therefore electrophile. Nucleophiles, electron pair is given, then they are liking the nucleus, therefore they are called as nucleophiles. Let's directly compare with each other. Okay, here we have nucleophiles, here we have electrophiles. Electron rich species that donate a lone pair that or pi electrons to an electrophilic center are called as nucleophiles. So they are electron rich, but they donate that electron rich pair. General nature, it is a Lewis base electron pair donor, usually carries negative charge or has lone pair or pi bonds. This is called as nucleophile. Okay, it has negative charge and it is carries pi bond, seeks the positive center. Common nucleophiles are OH minus ions. Hydroxide is a nucleophile. Okay, it is ready to give the electron pair, and it is being attracted towards the positive center, it is attracted towards the nucleus. Okay, and in similarly cyanide, ammonia, water, alkoxide and chloride, all these are common nucleosides. Direct statement based question, direct fact based questions are being asked from nucleophile. So hydroxide OH minus, cyanide Cn minus, ammonia NH3, water H2O, alkoxide RO minus and chloride ions, all these are nucleophiles. Exactly in contrast, there are electrophiles. Electron deficient species that accept an electron pair from a nucleophile. So electron is being accepted actually. So they are liking the electron, therefore they are electrophiles. Exactly opposite. Here the electron pair is being donated. Here the electron pair is being accepted. Usually carries a positive charge or is electron deficient. This is the rule. Common electrophiles are H plus ion, that is proton, and nitronium ion NO2 plus, boron trifluoride BF3, carbocation, that is R3C plus, and sulfur trioxide SO3. All these are the examples of common electrophiles. So common nucleophiles and common electrophiles you have to remember, and that's how direct fact based question can be coming in the examination and you will not miss the answer. How they work together, obviously electrophile, it converts into nucleophile, plus electrophile converts into new covalent bond, because one nucleophile is giving the electrons, an electrophile is accepting the electrons, and the new covalent bond is being formed. Let's see a quick comparison. Okay, nucleophile is electron rich, electrophile is electron deficient, usually negative or neutral on the nucleophile charge, whereas in the electrophile usually positive or neutral charge are seen. Donates the electron pair when it comes to nucleophile and accepts the electron pair when it comes to electrophile. It has a Lewis base, nucleophile has a Lewis base, and electrophile has a Lewis acid structure, and seeks the positive, here seeks the negative. More common examples are hydroxide, cyanide, ammonia, water, alkoxide and chloride when it comes to nucleophiles, and the common examples are proton, nitronium ion and boron trifluoride, carbocation and sulfur trioxide when it comes to electrophiles. Let's see about the strength also. Okay, the strength when it comes to the basic trend in the nucleophilicity, it means in the nucleophiles which basic structure, which base, which Lewis base has more strength. It means hydroxide is more stable than the alkoxide, then more than the cyanide, more than the iodide, more than bromide, more than chloride, more than water, more than ammonia. Again, this sequence also direct fact based question can be asked. And when it comes to electrophilicity, it means in the electrophiles the stability trend is obviously nitronium ion has more stability, strength more than the proton, more than the carbocation, more than we have what you call as RCHO ions, and more than the BF3. So these direct trend question can be asked. So you have to remember this one. Here we are having a previous year question about the nucleophile. Obviously, nucleophile is Lewis base, not Lewis acid. Okay. Look for electron flow. Nucleophile gives electrons. Electrophile accepts electrons. Strong nucleophiles and strong electrophiles. You have to remember all these ions. Electronic displacement effects, that is inductive effect. We are going to study what is inductive effect here. The key idea about this topic is permanent polarization along the sigma bond due to electronegativity difference. We are going to study this one in detail. So what do you mean by inductive effect? It is actually caused by electronegativity difference between the atoms. Okay, so there are two atoms, one requires an extra electron and one doesn't, which one has an extra electron. So depending upon there is electronegativity, that electronegativity will produce the inductive effect, that is called as I, produces partial charges and is transmitted through the carbon chain, decreasing with the distance. So this effect is passed along the carbon chain, decreasing with the distance. Okay, positive inductive effect, electron donating, and negative inductive effect means electron withdrawing. So if somebody is donating, then it has an extra electron, therefore it is positive, so pushes the electron density towards the rest of the molecule. Example is alkyl group plus one electron releasing, so methyl more than ethyl more than isopropyl more than butyl. So this is the sequence when it comes from decreasing order to from higher to lower level when it comes to inductive effect. And the same goes with the negative inductive effect, where pulls the electron density away from the rest of the molecule. Examples are these are their decreasing order. Okay, so you have to remember the positive inductive effect decreasing order and negative inductive effect decreasing order. Remember that is a polarization along the sigma bond. Okay, relative order of the inductive effect, these are the selected groups where more negative inductive effect, then a stronger electron withdrawal. And you should by heart all these sequence, direct sequence based questions, arrangement based questions can be asked. Okay, highly electronegative atoms or groups show strong negative inductive effect, and positive charge or multiple bonds increase the negative inductive effect. So these are some of the facts when it comes to inductive effect. You stop the video and study all the what you call as tables here. Almost all the tables are comparative in nature, and there is a previous year question also that are statement based. So these statement based questions sometimes can be confusing, so better revise this slide like 4 times and 5 times. So let's see some key takeaways. Okay, inductive effect operates through sigma bond and due to electronegativity difference. The positive inductive effect, electron donating alkyl groups, and negative inductive effect, electron withdrawing electronegative groups. And the order of the negative inductive effect you can see here has been given. Electrometric effect predominates over the inductive effect. Hyperconjugation stabilizes the carbocations. More sigma hydrogen bond, then there is a more stability. Resonance effect, M or R effect. See, these all are important characteristics of chemical bonding in the organic compounds. The key idea of the resonance effect or M or R effect is decolonization of the pi electrons. In the inductive effect, we studied about the sigma electrons, sigma bond, and here we are studying about the pi electrons, the decolonization, the delocalization of the pi electrons or lone pairs through a conjugated system, that is called as resonance effect, M or R effect. So let us see first of all what do you mean by resonance. What is resonance effect, M or R effect? The delocalization of pi electrons or a lone pair of electrons of a substituent through a conjugated system. So for example, there is a big chemical molecule, there is a system, but that system has an effect of a substituent, yani attached molecule to a main carbon compound. So there is a main carbon compound and there is an attached molecule that is called a substituent. So this substituent have an effect of localization of pi electrons or lone pair of electrons, and that operates through the p orbital and pi overlap. When it comes to inductive effect, we have studied about the sigma bond. Here it is resonant effect or M or R effect due to pi overlap, and that too seen from the effect of a substituent through a conjugated system. You have to understand and catch the keywords. Lone pair of N, that is nitrogen, delocalizes into the ring. There is a nitrogen here, okay? There is a nitrogen here. There is a nitrogen here. This nitrogen part, this ammonium ion part, is a substituent of this main organic compound. So this delocalizes into the ring. Electron density increases at the O and P positions, okay? Ortho and para positions. At these positions, the electron density is increasing. That type of effect is called as resonance effect. Now, positive resonance effect and negative resonance effect. Let's see. The positive R effect or electron donating groups and negative R effect, that is electron withdrawing groups. This rule applies at an every stage, even at the inductive effect also. If it is positive, then obviously it is having electron donating groups, and if it is negative, then electron withdrawing groups. The electron donating groups, so remember, positive effect means electron donating. The same we have seen in the inductive effect also. But this is going to increase the electron density into the conjugated system by resonance. Remember, this resonance effect is by conjugated system. Conjugated system means for an organic compound like a ring structure, a cyclic compound, there is an attached substituent, an other group, like for example this nitrogen group, and that group is going to show some electron density effect on that ring, on that organic compound. That type of electron density effect is called as resonance effect. So positive resonant effect and negative resonant effect. The positive resonant effect increases the electron density on ring, activates the ring towards the electrophilic substitution, and the negative electron resonance effect decreases the electron density on ring, deactivates ring towards electrophilic substitution. So this is about the R effect. Okay, R or M means resonance or delocalization. Positive R electron donation by resonance, and negative R electron withdrawal by resonance. Comparison of the I effect or R effect. Let's see the compare. This is very important. Okay, inductive effect through sigma bonds, resonance effect through pi bonds or lone pairs. Inductive effect present in all molecules. Resonant effect needs conjugation. It means p orbital and pi overlap has to happen. Inductive effect decreases rapidly with distance, and resonance effect works over entire conjugated system. Inductive effect decreases rapidly with distance due to electronegativity difference, and this is due to delocalization of electrons, and these are the examples. Okay, here is a NEET question here given, previous year question, NEET questions. Stop the video and study all this one in a proper way. Activating groups of the ortho para directors, you have to by heart this one. Deactivating group in the meta directors, these are the deactivating groups. So direct activating groups and deactivating group, direct fact based question can also come in the exam. Okay, and order also has been given here. This order you have to write 10 times and by heart, then only you can answer this one. Hyperconjugation, there is no bond resonance. Okay, it means the delocalization of sigma electrons, usually CH bond, with an adjacent empty p orbital or pi bond. Now in the inductive effect we studied about the sigma bonding, and in the resonance effect we have studied about the p orbital pi bond delocalization. In the hyperconjugation we are going to study about the delocalization of sigma electrons with the p orbital of the pi bond. So what is hyperconjugation? Delocalization of sigma electrons of CH bond, that is on the alpha carbon, the adjacent carbon, to an empty p orbital or pi bond or positively charged carbon. also called as no bond resonance. Okay, so this type of resonance, this type of effect is called as hyperconjugation. Remember, this is between sigma electrons from CH bond and with the empty p orbital. There is no proper bonding here because the p orbital is also empty, but there is a delocalization happening with the alpha carbon, that is adjacent carbon, and also called as no bond resonance, represented by curved arrows from CH sigma bond to the empty p orbital or pi system. Effects of hyperconjugation. What happens here is this hyperconjugation stabilizes the carbocations, alkenes, and free radicals. So it is helping for stabilization for the carbocations, alkenes, and free radicals. More number of alpha hydrogens give rise to greater hyperconjugation, that give rise to greater stabilization. It opposes the electron withdrawing effect of positive charge or pi bond, donates the electron density. Okay, so general rule is more alpha carbon and H, then there is more hyperconjugation, more stability. Number of alpha hydrogens and stability carbocations can be seen because it is having only one carbon and alpha and hydrogen, therefore it is having less stability, so therefore it is increasing. Stability order of the carbocations is tertiary more than secondary, more than primary, more than methyl. Okay, now how this hyperconjugation occurs. Okay, let's see example. Okay, the sigma bond of the carbon hydrogen bond give rise to and has an effect on the empty p orbital on the C plus, that is on the alpha carbon, stabilizes the carbocation. Okay, so this is the effect. Now these are the previous year NEET questions. This is statement based question. Okay, stop the video here, study properly, see the diagram also. You have to see even with the conjugated system also how there is an effect of hyperconjugation. Okay, and no bond resonance. The silent features are involves the sigma bond, usually CH bond, and an adjacent p orbital or pi bond, also called no bond resonance. No actual bond is formed. Hyperconjugation decreases electron deficiency or positive charge or radical character. Greater the number of alpha and H atoms, greater is the stabilization. Direct stabilization sequence can also be asked. Remember, inductive effect is about the sigma bond, and the resonance effect is about the MTP orbital and pi bond, and hyperconjugation is about the delocalization of the sigma electrons, usually of the CH bond with the MTP orbital. Electromeric effect. Okay, the idea about the electromeric effect is presence of an attacking reagent. That's it, you have to remember this one. Electromeric effect means how a reagent is going to attack. This is the main concept. Okay, let's see the definition. What is electromeric effect? First of all, this electromeric effect is temporary and reversible, occurs only in the presence of attacking reagent, a electrophile or a nucleophile, involves complete transfer of pi electrons of a multiple bond towards or away from the attacking reagent. So consider that to an organic compound, beside that organic compound there is an attacking reagent. It means either a electrophile or a nucleophile. Then the transfer of pi electrons of a multiple bond towards or away the attacking agent is called as electromeric effect. You can see the diagram also. Okay, represented by curved double-headed arrows. Okay, so A, B are atoms of the multiple bonds, and there is a electrophile here. It means it is a attacking reagent. So when it is present, then there is a transfer of pi electrons. This effect of transfer of pi electrons in the presence of an attacking reagent is called as electromeric effect. The types of electromeric effect, again, the positive effect and the negative effect. Positive electromeric effect means pi electrons of the multiple bond are transferred towards the attacking reagent. It is towards. Okay, and negative effect means it is away from the attacking reagent, shown by groups having lone pair on the atom of multiple bonds. The positive effect is shown by the presence of lone pair, and the negative effect is shown by the presence of the uh, electron withdrawing substance. It stabilizes the positive charge, it stabilizes the negative charge. Positive, positive, negative, negative. That is easy to remember. Okay. Now we have to compare the inductive effect with the electromeric effect. The inductive effect is permanent in nature, electromeric effect is temporary in nature. The inductive effect is due to the electronegativity difference, and electromeric effect is due to the presence of attacking reagent. The inductive effect has partial shift of sigma electrons through sigma bond, and the electromeric has complete transfer of pi electrons of the multiple bonds. So you have to study this table. The comparison between the inductive effect and the electronic effect is very important. And you can see there are some previous year questions also. Those are statement based. Statement based questions are direct NCERT line questions, which I have given in this slide also. So the key takeaways are: the required attacking reagent, either electrophile or a nucleophile, in order to show some electromeric effect. It is a temporary and it is a reversible effect, and complete transfer of pi electrons. Positive electromeric effect means towards the reagent, and negative electromeric effect means away from the reagent. Electromeric effect predominates over the inductive effect. You have to remember all those things. Remember these alkyl groups also, these functional groups also, and direct questions, fact based questions, NCERT lines are being asked in the exam. I would request all of you students to subscribe to this channel, like this video, and comment also. Comment your doubts, and if you have any doubts in this topic, or you have any doubts pertaining to another topic also, you can ask me. So purification methods, it means how to separate the desired component from the physical impurities and the chemical, depending upon the chemical properties. So the purification methods, techniques, and PYQs are given in one tabular form here. See, first is sublimation. So the main principle is actually solid is being converted into vapor directly. Some solid is changed directly from solid to vapor on heating and redeposit on cooling. Examples are camphor, naphthalene, and benzoic. So in order to purify camphor, naphthalene, benzoic, or in order to extract something which are present within naphthalene, benzoic acid, and camphor, we use the process called as sublimation. So you have to know the name of the method, what is the principle of the method, and also what are the examples or application examples of that method. And the diagram, you can see solid which is impure, heated gives rise to vapor, after cooling gives rise to pure solid, that is deposited. So the vapor things are impurities and they will go outside. Okay, so benzoic acid can be purified by, the answer is crystallization. Here benzoic acid is not purified, some other structure is purified here. Okay, but benzoic acid is vapored out. Don't get confused. Crystallization, difference in solubility depending upon the chemical structures which are, yes. In the same way, all the other methods have to be studied. Crystallization, it happens because of the difference in the solubility. The solubility of a substance increases with temperature. On cooling, pure crystals separate out. Purification of the solid organic compounds, example benzoic acid. You can see in the diagram also. In the same way, read other methods also. All the methods have been given here. Read the examples, like for which type of chemical, which type of separation methods or techniques are used. These are direct questions. Okay. So after studying the purification method, their principle and their application and also examples, here are a few of the previous year questions. You can see that a match the following question has been asked, and if you only remember the examples, then only you can finalize which example is actually used for what type of separation methods. There are few other questions also, the reason has been asked here. A steam volatile organic compound, it's all about obviously distillation, but at that steam distillation, what happens with the vapor? That kind of a deep concept question has been asked, and other questions are very direct in nature. Okay, so just stop the video here and study all these previous year question, and also again go to your previous slide and study again. Interfering reactions, these are interfering reactions. Okay, for example, cyanide plus uh, silver, gives rise to silver cyanide. It has white precipitate. In the same way, you also have sulfur, okay, and that gives black precipitate. Okay, you just stop the video here and study it multiple times, and that's only you will get into perfect when it comes to purification methods. Here, some key takeaways. The method based on the physical and the chemical properties of the components should be selected. Boiling point difference is the key in the distillation techniques. Boiling point, vapor, all these things will be used in the examination. Steam distillation is used for steam volatile compounds immiscible. It means not soluble with water. Reduced pressure lowers the boiling point, useful for heat sensitive liquids. Okay, so for those students in which the boiling point is high, or those substances where they are heat sensitive, then if you decrease the pressure, automatically obviously these things will decrease. Chromatography is used for separating and analyzing the complex mixtures. So you have to study about the previous year questions and also understand the reason behind what type of method is used for what type of substance. Now comes the qualitative analysis. It means the quality of that compound has to be known. That type of analysis, that type of observation or separation is called as qualitative analysis. The main test here is Lassane's test. Okay, let's see the principle of this qualitative analysis. Organic compounds contain the covalent elements nitrogen, sodium, xenon, and potassium. In Lassane's test, the compound is fused with the sodium metal. You have to understand that the special condition when it comes to the Lassane's test, it is sodium. So it is fused with the sodium metal. Covalent elements, that is nitrogen, sodium, xenon, and phosphorus, converted into ionic compounds in the sodium extract. Fusion reactions. Let's see this fusion reaction. You can see here sodium with cyanide, okay, sodium cyanide, sodium sulfide, sodium halide, and sodium phosphide. The ionic compounds are soluble in water and form the sodium extract. That is the principle. We are going to make that compound into an extract level, and that is how you will come to know about the quality. Let's see the test for different elements. For nitrogen, boil the sodium extract with iron sulfate solution, filter, then acidify with iron chloride solution. It gives Prussian blue color. For sulfur, there are two methods. One is add lead acetate solution in acetic acid. Black precipitate is produced, and add sodium nitroprusside solution and make alkaline. Violet color is produced. When it comes to halogen, add silver nitrate solution in the presence of nitrite. After acidification, white precipitate is formed when it comes to chlorine, pale yellow precipitate is formed when it comes to bromine, and yellow precipitate is formed when it comes to iodine. So you have to understand which element is used for which type of test and what is the observation, the color of the precipitate for what element. Direct match the following question can be asked with these names. So these are pure memory based, you have to by heart. If both nitrogen and sulfur are present in an organic compound, what will be the observation when sodium thiocyanate is added to the extract and then treated with iron solution? So obviously when S is present, it forms iron in extract, and with cyanide it forms thiocyanate, and with iron it forms iron thiocyanate. The color is blood red color. In presence of the iron ion, ferric ions, the sodium cyanide, sulfur cyanide gives blood red color due to the formation of the complex ion, that is ferric sulfur cyanide. Why is Lassane's extract boiled with concentrated nitric acid before testing for halogens to decompose the sodium cyanide and sodium sulfide? Otherwise, the cyanide ions and sulfide ions would give precipitates with silver and interfere in detecting halides. NEET previous year question, there is a match the following. You have to understand that one. The key takeaways about the qualitative analysis are: fusion with the sodium converts covalent elements into ionic compounds. Sodium extract is tested for sodium, nitrogen, sodium, xenon and phosphorus using specific reagents. Always acidify the extract with concentrated uh, nitric acid before testing for halogens to remove interferences. Characteristic colors or precipitates confirm the presence of specific elements. Lassane's test is a powerful method for qualitative analysis of organic compounds. Quantitative analysis, it means how do you determine the percentage or the amount or the quantity of a compound present in an element present in an organic compound. One is carbon and hydrogen. In order to have the quantitative analysis of carbon and hydrogen, we use combustion method. The compound is burnt in excess oxygen, carbon dioxide and water formed are weighed. Then percentage of carbon is equals to 12 into mass of carbon dioxide into 100 by 44 into mass of compound. Similarly, percentage of hydrogen is equals to 2 into mass of water into 100 by 18 into mass of compound. Here an example problem has also been given. Nitrogen. In order to have the quantitative analysis of nitrogen, we use the Dumas method. The compound is heated with copper oxide. Nitrogen molecule evolved is collected and measured over water. So volume of the nitrogen at standard temperature and pressure STP is equals to volume in ml is equals to P1 V1 into 273 by 760 into T1, where the P1 stands for pressure of the dry nitrogen in mm and V1 stands for volume of the nitrogen collected per ml and T1 stands for temperature in Kelvin. So percentage of nitrogen is equals to 28 into V into 100 by 22,400 into mass of the compound, where V is equals to volume of the nitrogen at standard temperature and pressure in ml. Previous year NEET question, you can see that 0.25 gram of an organic compound give 40 ml of nitrogen at 300 Kelvin and 725 mm pressure. Aqueous tension is 25 mm. Calculate the percentage nitrogen in the compound. As you can see in the question, he has already given the pressure and there is a pressure difference also. He has given one pressure of the compound as 725 mm and he has also given the pressure, that is aqueous tension, of the 25 mm. So obviously the total pressure will be 725 minus 25, 700 mm, and the volume has also been given being as 40 ml of nitrogen molecule, and the temperature has given that 300 Kelvin. In the formula obviously we are going to use the temperature in Kelvins only, so you need not to convert that into Celsius and Fahrenheit. If he gives the question in Fahrenheit and Celsius, then you have to convert that temperature into first into Kelvins, then only you are going to apply that numbers in this formula. That's how you solve the Dumas method quantitative analysis in the organic chemistry. The key takeaways are: carbon dioxide, the carbon is determined from carbon dioxide and H is determined from water, and nitrogen is collected and measured through Dumas method. Use correct conditions of STP for accurate calculation, even the physical quantity also. Always supply formulas carefully with correct units. Now, one more method of this quantitative analysis is Geldas method. Okay. In this Geldas method, what do we do? Let's see properly. The compound is digested with the concentrated sulfuric acid in presence of catalyst, and nitrogen is converted into, yes, ammonium sulfate. This is Geldas method. So on making alkaline, the ammonia is liberated and distilled. Ammonia is absorbed in a known excess of standard H2SO4, and the excess acid is back titrated with standard sodium hydroxide. So the percentage of nitrogen is equals to 1.4 into M, where M stands for the normality or the morality of the H2SO4 and sodium hydroxide into 2V minus V1 by mass of the sample in grams. So in which ammonia is being distilled, excess hydrogen sulfur, you can see that in the diagrammatic presentation also. Geldas method cannot be used for compounds containing nitro group, azo group, or ring nitrogen. They can be used only when the conditions are this one. In the presence of nitrogen, nitrogen is converted into ammonium sulfate on making alkaline, then ammonia is liberated and distilled. So this method cannot be used for nitro groups, azo groups, and ring nitrogen groups. The previous year NEET question, an example you can see here, zero point 0.7 grams of soil sample on the GELDAS estimation of nitrogen. The liberated ammonia completely neutralized 10 ml of 1 molar sulfuric acid. Calculate the percentage of nitrogen in the soil sample. So mass of the sample, volume has been given, molarity has given. So step 1, you have to find the normality of sulfur. Then step 2, since all the acid is used to neutralize the ammonia, excess acid is 0. So V1 is 0. So you have to add all these into this simplification and you will get the number. Which of the following compounds cannot be estimated by Gildas method? As we have told that the nitro group cannot be estimated, and also the pyridine group also cannot be estimated. Okay. The quantitative analysis of halogen, sulfur and oxygen is a bit different. For the halogens, it is called as Carius method. You should remember the name, scientific names also, and also the formula. We actually can explain in detail how we have reached to this conclusion of the formula. ये formula कैसे बना है ये भी हम पढ़ सकते, but for revision sake you have to by heart this formula only. Now we don't have time. So percentage of X at means halogen is equals to atomic mass of X into mass of AgX into 100 by molar mass of AgX into mass of the compound. So silver nitrate, Ag, it means silver. So silver nitrate precipitate, silver chloride, bromide, such type of halogen precipitate will be formed. Vicarious method, heated with silver nitrate is sealed tube, then there is a precipitate insoluble is formed. There was a NEET question also. You can solve that question on your own. Now sulfur, percentage of sulfur is equals to 32 into mass of the barium sulfate into 100 by 233 into mass of the compound. When it comes to sulfur, the percentage of sulfur is equals to 32 into mass of barium sulfate into 100 by 233 into mass of the compound. How do we have arrived to this formula? That's a very detailed concept. Now we are only seeing the revision part. So you have to by heart the formula as of now. Okay, when it comes to oxygen by difference, percentage of oxygen is equal to 100 minus percentage of carbon plus hydrogen plus nitrogen plus sulfur plus halogen plus phosphorus. So in that way you can easily count the percentage of oxygen by difference. You can see the example also. The key takeaways are halogens are estimated as insoluble silver halogen Carius method. Sulfur is estimated as barium sulfate precipitate gravimetric method. All formulas are based on mole ratios. Use correct molar masses and units carefully. NEET PYQs help learn application of the formulas. High yield points from the previous year questions. Okay, let's see. Boiling point of pentane isomer, this was the last year question. Okay, the increasing and decreasing order has been given, and that is all what he will ask. N pentane has more than compared to isopentane compared to the neopentane, and the branching decreases the surface area, decreases the intermolecular forces, and that's how it gives rise to boiling point to decrease levels. So the increasing and decreasing order of the boiling point according to the branching has been asked previously. Okay, and there is also this question about stability. The stability increases due to hyperconjugation and positive inductive effect. Therefore the tertiary butyl carbocation is most stable. So it is from increasing order. IPAC name, the number of sigma bonds and pi bonds, you have to calculate all this one. And hybridization sequence, most reactive towards the electrophilic separation of the ortho and para nitrophenol, steam distillation, dihedral angle of least stable ethane conformer, 0 degree eclipsed conformation, and Lassane's test, Prussian blue is in nitrogen present, then it gives the Prussian blue color, and tautomerism required sigma alpha H and bridgehead H does not participate. Keto form, enol form. So these things you have to remember for quick revision. Classification of hydrocarbons. So hydrocarbons C and H only. So hydrocarbons, alkanes, alkenes, alkynes, and aromatic hydrocarbons all are to be covered here. So when it comes to hydrocarbons, it means those organic compound which has H and C, hydrogen and carbon as their main component in all the uh, categories. So they are saturated alkanes, unsaturated alkenes and alkynes, and aromatic arenes. So saturated alkenes means that the C single bond are present. It means the formula is CnH2n plus 2. You have to remember this formula thoroughly. You should not ever forget this one. The formula of the alkenes is CnH2n plus 2. It means there is a single bond between the two carbons. These type of hydrocarbons are called as saturated carbon hydrocarbons or alkanes. Now comes the unsaturated hydrocarbons. The unsaturated hydrocarbons are alkenes C double bond C and alkynes C triple bond C. So in the alkenes CnH2n is the formula. There is a double bond, and in the alkynes there are Cn2n minus 2. Therefore that there has a triple bond in between the two carbons. Aromatic hydrocarbons are also called as arenes. Examples are benzene and derivatives. Now, let's compare the hydrocarbon classes. Okay, so alkanes, alkenes, alkynes, and aromatic hydrocarbons are called as arenes. So the general formula of the alkanes is CnH2n plus 2 acyclic and CnH2n cyclic. And alkenes general formula is CnH2n. It means if non-cyclic CnH2n, it is alkene, and cyclic CnH2n, it is alkane. And alkynes have the formula CnH2n minus 2, and aromatic arenes have CnH2n minus 6 mononuclear. The bond type in the alkane is carbon-carbon single sigma bond, and the bond type in alkene is carbon double bond carbon sigma plus pi bond. And in the alkynes, carbon triple bond carbon sigma plus 2 pi bond. And in the aromatic arenes, delocalized pi system can be seen. The hybridization in alkanes is sp3, and alkenes is sp2, and alkynes is sp, and aromatic arenes is sp2 hybridization. So alkenes and arenes have same type of sp2 hybridization. The shape of the alkanes are tetrahedral, the alkenes shape is trigonal planar, and alkynes shape is linear, and the aromatic arenes shape is trigonal planar, same as alkenes. Physical state is C1 to C4. The alkenes are gases, alkenes also gases, alkynes also gases, and the aromatic arenes are liquids, benzene. Solubility in water, all the three are insoluble. Benzene is slightly soluble. Combustion, burn with sooty flame, all these burn with the sooty flame. So NEET frequently test the physical properties like boiling point, solubility, and chemical reactivity differences between these classes. No general formulas, hybridization, and typical reactions well. Higher boiling point, alkanes has less compared to alkenes, has less compared to alkynes, has less compared to arenes. For similar molar mass also. Reactivity towards the electrophilic additions, alkenes is higher than the alkynes. Aromatic compounds undergo electrophilic substitution, not addition. General structures you can see here, alkane example has given, alkene structure, alkyne and aromatic benzene structures are also given. You can stop the video and revise the whole slide again. The structure of alkanes, paraffins, the generalized formula is CnH2n plus 2. The structure and hybridization. Saturated hydrocarbons with only C single bond C and C single bond H. Single bonds, carbon is sp3 hybridized, tetrahedral geometry, bond angle is 109.5 degree and bond length is 154 pm, and for carbon single bond carbon, and for carbon single bond hydrogen it is 112 pm. The nomenclature. Alkanes show chain isomerism. Therefore, 2 isomers, 3 isomers, 5 isomers, respectively for C4, C5, and C6. Number of structural isomers increases with carbon number, and classification of carbon atoms. Attached to first carbon, such type is called as primary. If attached to second carbon, it is secondary. If it attached to third carbon, it is tertiary. And if attached to fourth carbon, then it is quaternary. The previous year question also has been given boiling point order of the isomers. Branching increases the spherical shape, smaller surface area, weaker van der Waals forces, and lower boiling point. Therefore, answer is A. The correct order is 1 is higher than, 2 is higher than 3, because 1 has less branching compared to the 2 and compared to 3, and if the branching is less, then the boiling point is higher. One more previous year question, again boiling point was asked here. You can stop the video and assess the branching there. Alkanes are saturated hydrocarbons with formula CnH2n plus 2. Carbons are sp3 hybridized with tetrahedral geometry of 109.5 degrees angle. Branching decreases the boiling point due to reduced surface area. NEET frequently tests the boiling points, isomerism and carbon classification. I would like you all to please subscribe to my channel and like the video and comment in the comment section if you have any doubts in the slides I have explained, or at least if you want any other topic from my side to get explained, then I can explain that. I can take out time, and please do share to your friends also, to NEET aspirants. Help me help students. Preparation of alkanes. How do you prepare these alkanes? Obviously, there are 5 methods. You have to just by heart all these 5 methods and remember the important key points. Hydrogenation, reduction of alkyl halides, Woods reaction, decarboxylation, and coal-based electrolysis. Remember, whenever there is named reaction or scientific reaction, then that named reaction is very, very important. Hydrogenation, the name itself tells the reaction with the hydrogen. Reduction of alkyl halides, the name itself tells that it is reduced with the combination of alkyl halides. Woods reaction, it is very important. You can see here, Woods reaction. Okay, the condition for Woods reaction is dry ether, and the limitation is gives even number of carbon atoms only. So 2Rx plus 2Na gives rise to Rr plus 2NaX, and 2CH3Br plus 2Na gives rise to CH3CH3 plus 2NaBr. Woods reaction is important. As simple you have to by heart is, Woods reaction is a type of preparation of alkanes method, and the condition is it has to have dry ether, and the limitation is gives even number of carbon atoms only. Decarboxylation, obviously the condition is calcium oxide and heat. RH has one carbon less than the acid, that is decarboxylation reaction. Coal based electrolysis, obviously the condition is electrolysis, and even number of carbon atoms formed. Methane is not formed through coal based electrolysis. The weight in gram of 2 moles of the organic compound obtained by heating sodium ethanoate with sodium hydroxide and calcium oxide, it means decarboxylation, is, you have to calculate sodium ethanoate under the presence of sodium hydroxide and calcium oxide gives rise to methane. So molar mass of the methane is 16 gram. So 2 moles means 32 grams. A hydrocarbon A reacts with bromine to give an alkyl bromide via substitution. The alkyl bromide on treatment with sodium in dry ether gives a gaseous hydrocarbon containing less than 4 carbon atoms. The hydrocarbon A is. So the hydrocarbon A is methane, because the even number is not. Woods reaction of the CH3Br gives ethane. Gaseous hydrocarbon is less than 4 carbon atoms, hence the answer is CH4, that is methane. Alkanes are prepared by reduction, coupling and decarboxylation methods. Woods reaction gives even number of carbon atoms in the product. So these preparation of alkenes is very important question, mostly expected in the exam also. You should remember what type of method is being used, what is the reaction going on, and what is the condition required, and what are the limitations. The key takeaways are alkenes are prepared by reduction, coupling and decarboxylation methods. Woods reaction gives even number of carbon atoms in the product. Coal-based electrolysis also gives even number of carbons, no methane formed. Decarboxylation gives an alkane with one carbon less than the acid. NEET always loves application-based questions from the preparation methods. So these are the preparation methods, not only just method and the alkane, but he will give application-based questions. So try to practice that one according to the previous year questions. The chemical properties of alkanes. There are many properties. Let's see few of them. Halogenation, free radical substitution. So order of reactivity is more highest for fluorine, then chlorine, then bromine, then iodine. And order of H abstraction, it is a hydrogen abstraction, is highest in the tertiary more than secondary more than the primary. So the general reaction is RH alkane plus chlorine gives rise to RCl plus HCl alkyl chloride. So this is a halogenation free radical substitution reaction. Mechanism can be easily studied here. It has some initiation, then propagation and termination. The tertiary has a higher order of abstraction, H abstraction, compared to the secondary and then compared to the primary. So this is a very simple halogenation reaction of the alkane. So the second is combustion. What happens here is complete combustion of alkane gives carbon dioxide and water with a clean non-sooty flame. Incomplete combustion gives carbon monoxide or carbon with sooty flame. So when it comes to combustion, these alkanes are going to give you carbon dioxide and water with a clean non-sooty flame. Incomplete combustion gives this one, you have to remember. Aromatization, that is reforming N-hexane under 773 Kelvin temperature and under the presence of Cr2O3 and Al2O3, it gives benzene plus 4H2, and heptane under same conditions gives toluene plus 4H2. So how do you produce benzene and toluene? Through aromatization, that is reforming of the alkanes. Next comes the isomerization. N-alkanes under the anhydrous aluminum chloride or HCl presence, it gives branched alkanes. Example, N-butane give the isobutane, that is also isomerization. So for isomerization, it needs aluminum chloride or hydrochloric acid, and for aromatization, it needs chromium oxide and aluminum oxide. So that gives rise to benzene and toluene. You have to remember which reagent is used for what type of reaction and what is the product being formed. Moving on, the fifth type of chemical properties of alkane is pyrolysis, also called as cracking. What happens is these higher alkanes are converted into lower alkanes and alkenes. So they are converted into lower alkanes and alkenes in the pyrolysis. Okay, so there are five types of reactions you have to see. These are the properties of alkanes, like halogenation, combustion, aromatization, isomerization, pyrolysis. There are previous year questions also. You can see here there are many previous year questions. The alkene which can be oxidized to an alcohol by KMnO4. The alkene which on monochlorination gives only one monochloro product is. There are many. All 12 H atoms are equivalent, hence only one monochloro product is formed. So it is neopentane. So you have to try to have some logic that you know what happens during halogenation, what is happening during the oxidation. These type of questions are asked. Okay, so liquid hydrocarbons can be converted into gaseous hydrocarbons by, obviously, by cracking, that is pyrolysis. This cracking or the pyrolysis breaks larger hydrocarbons into smaller alkanes and alkenes, many of which are gases. So the lower alkanes are always gases. So these liquid is converted into the gaseous type of alkenes through cracking or pyrolysis. So the key takeaways are: alkenes undergo free radical substitution, halogenation in presence of light or heat. Alkenes burn with a clean flame. Incomplete combustion gives soot. Aromatization or reforming converts the alkanes to arenes in presence of catalyst. What are the catalysts? You can see there, Cr2O3 and Al2O3. So, and the N-alkenes can be isomerized to branch the alkenes also. This branching happens through isomerization, and that isomerization happens in the presence of anhydrous aluminum chloride. Cracking or pyrolysis produces lower alkanes and alkenes. Moving on, conformations of ethane. So taking primary example, ethane, which is one of the most common hydrocarbons. So the conformations of ethane are two: one is staggered and another is eclipsed. So there is a direct comparative table here. It is very important. The staggered conformation of the ethane H atoms are, it is more stable, and the eclipsed conformation of ethane is less stable. H atom, that is hydrogen atoms, are farthest apart. H atoms are aligned. Dihedral angle 60 degree. Dihedral angle is 0 degree. No torsional strain. Maximum torsional strain, minimum potential energy, and maximum potential energy. There is a direct comparison here, but if the statement comes in a sentence format, every student have chances to get forget. So you have to be thorough in these things, that how staggered ethane and eclipsed ethane has effects, and what are their main properties. You can see in the this graphical presentation also, staggered has potential energy lower. You can see here in the graph also, if the y-axis is potential energy, then the at the stagger stage the potential energy is lower, and at the eclipse the potential energy is maximum. So that you have to understand. The second important confirmation is Newman projection. Again, in the same condition where you like staggered and eclipsed, the Newman projection can also be studied. Okay, the front carbon H at 12, 4 and 8 o'clock, back carbon and hydrogen at 2, 6 and 10 o'clock. This direct fact based question can also come here. Let's see about the important terms that have to be explained, because sometimes direct terms can come in as part of the definition, and those considered very basic question, but it will be very hard to answer. So stop the video here and study all these important terms when it comes to uh, what do you call as hydrocarbons. Okay, key takeaways are: staggered 60 degree is most stable, no torsional strain. Eclipse 0 degree is less stable and maximum torsional strain. Energy difference is 12.5 kg per mole, and rotation about carbon carbon single bond interconverts the conformations. Moving on, conformations of N-butane. So key conformations of N-butane, you have to remember the conformations of ethane also. There it was staggered and eclipse. Here the key conformations of N-butane are, okay, so anti, that is most stable, gauche, that is less stable, eclipsed also less stable, and least stable is eclipsed. Okay, now the dihedral angle of the anti most stable is 180 degree, and the dihedral angle of the gauche less stable is 60 degree. Eclipsed is less stable and the dihedral angle is 120 degree, and the eclipse least stable dihedral angle is 0 degree. So methyl groups are 180 degree part in the anti conformation, and methyl groups are 60 degree part in the gauche conformation, and methyl eclipsed with hydrogen and methyl eclipsed with methyl in the eclipsed least stable format. So you have to do some comparison also. So potential energy diagram also, you can see if we draw the dihedral angle here and the potential energy on the y-axis, you can see that Gauche has a least potential when it comes to anti and Gauche, which are alternating, but the eclipsed has the highest. That goes same with the ethane also, which we have studied in the previous slide. So the key takeaways are: rotation about the carbon single bond gives different conformations. Stability order is anti 180 degree is more stable than gauche, 60 degree is more stable than eclipsed 120 degree, and that is also more stable than the eclipsed least stable 0 degree and 360 degree. Reason is steric hindrance, methyl methyl repulsion, and torsional strain. These are the reasons for these less stability. Anti-conformation has minimum steric and torsional strain, therefore this anti-conformation is most stable. What do you mean by steric hindrance? Repulsion between bulky groups when they are close to each other is called as steric hindrance, because there is least steric hindrance in the anti group, that is why it is more stable. You can study the previous year question also, and comparison of the conformations can be seen here. Direct statement based or diagram based or match the following type of questions can be expected from these conformations of the N-butane. So in the previous slide we have studied about the conformation of ethane, and in this one conformations of the N-butane. Now comes the alkenes. The formula of alkenes is CnH2n. The structure of double bond, C carbon double bond carbon consists of one sigma bond and bond, that is sp2 overlap, and one pi bond sideways overlap of the pb orbitals. The bond length is 134 pm, shorter than the carbon single bond carbon bond 154 pm. So the bond length is shorter here, and bond angle is not equal to 120-degree. Trigonal planar sp2 hybridization, restricted rotation about the carbon double bond carbon due to pi bond leads to geometrical isomerism. So here in the previous chapter also we have studied about the isomerism. Here we are having geometrical isomerism. The reason behind the geometrical isomerism is carbon double bond carbon. So key structural data: hybridization of carbon is carbon double bond carbon sp2, bond angle is 120-degree. The carbon double bond carbon bond length is 134 pm. Carbon single bond length is 154 pm, and carbon and hydrogen bond length is 108. Direct fact based question, memory based questions are expected, so stop the video here and repeat multiple times. Important terms you have to go: sigma bond, pi bond, what do you mean by sp2 hybridization, all things you have to revise again and again. Now, the nomenclature and isomerism. For the structural or the constitutional isomerism, obviously we have studied the nomenclature earlier also. You just stop here and revise. Which one of the following compounds can exhibit the geometrical isomerism? Okay, you have to understand that if it is ene alkene, that is but 2 ene or 3,4 dimethyl x 3 ene. Explanation why: because geometrical isomerism requires carbon of double bond to have two different groups. So only option D satisfies that there is a carbon with double bond and having two groups. Therefore, that is the reason here. Now, the restricted rotation in 2-butene is due to, the reason for the rotation is sidewise overlap of the p orbital, that is pi bond. So these are the answers. You stop the slide here and repeat all these alkenes and their formula, their structure, and the important terms, nomenclature, and isomerism, and the previous year questions thoroughly. So now let's study preparation of alkenes, CnH2n. Okay, there are four methods. One is partial reduction of alkynes, dehydrohalogenation, also called as beta elimination, dehalogenation of vicinal dihalides, and four, acidic dehydration of alcohols. So let's see what do you mean by partial reduction of alkynes. Okay, the partial reduction of alkyne, the word itself tells that the alkynes are reduced but at a partial level. What does it need? It needs hydrogen ions and also H2, and it needs a Lindlar's catalyst. What is Lindlar's catalyst? Could be a direct question in the NEET. Lindlar catalyst, that is lead or barium sulfate poisoned with quinoline, adds the H2 and then it converts the cis alkene. So Lindlar's catalyst is used in the presence of the hydrogen in order to convert the alkynes into the reduction of alkynes to the production of alkenes. Second is dehydro halogenation. D and hydro, the word you have to break down. What happens here is beta elimination. It means removal of the H from the beta carbon and X from a alpha carbon. So this removal and elimination both are same actually at of the X, it means of a compound. Okay, X from the alpha carbon, both alpha carbon के पास से एक remove हो रहा है और बीटा कार्बन के पास से भी आपको जो है ना H remove हो रहा है. This called as dehydrohalogenation. Okay, so the ease of elimination order is highest, very easy is for tertiary, more than secondary, more than primary. You can see the diagram there also. Okay, so by use of the halogen carbo hydrocarbons along with the bromine. Okay, so this happens, alcoholic KOH and heat is required. Okay, the dehalogenation of vicinal dihalides. So what do you mean by the dihalides? Obviously there are two halogens, and removal of the two halogen atoms from adjacent carbons to form the double bond. Okay, so now comes the acidic dehydration of the alcohols. So you take any alcohol under the concentrated sulfuric acid and heat, then the elimination of water from the alcohol happens, and that is called as acidic dehydration of alcohols. So these are four preparations of alkenes. Important terms: partial reduction, it means addition of H2 in such a way that triple bond is converted to double bond. That is called as partial reduction. Lindlar's catalyst is a mild catalyst that stops reduction at alkene stage and gives a cis alkene. Dehydrohalogenation, elimination of HX, that is hydrogen and halogen, from adjacent carbons. Beta elimination, H is removed from the beta carbon next to the carbon bearing leaving group. Vicinal dihalides, it means compounds having two halogens on adjacent carbons. Dehydration is removal of water from alcohol to form alkene. So here you can see there is a previous year question also, like which of the following is not a correct method for the synthesis of alkenes. Moving on. Chemical reactions of alkenes. So there are many chemical reactions we are going to study one by one. Okay, electrophilic addition of reactions. So what happens, it is a very general mechanism. Whenever there is an electrophile near a alkene, there happens a addition, and for in order to follow that one also there is a rule. There are basically two rules. Okay, so what is rule? One is Markovnikov's rule and another is anti-Markovnikov's rule. One thing you have to remember is Markovnikov rule or anti-Markovnikov rule is seen in the electrophilic addition reactions of the alkenes. So what is here happening? Negative part adds to carbon with fewer H atoms. So wherever there is a negative part, it is going to add to carbon with lesser hydrogen atoms. And anti-Markovnikov's rule, also called as peroxide effect, only with hydrogen bromide in the presence of peroxides gives product opposite to the Markovnikov. So this is called as Markovnikov's rule and anti-Markovnikov rules. You have to remember this properly. This is seen in the chemical reaction, especially the electrophilic addition reactions of alkenes. Second type of chemical reaction is addition of halogens. So bromide reddish brown after the in order to test for unsaturation decolorizes to colorless. So these bromide, which of the following does not decolorize bromine water, C6H6, it does not colorize, it does not decolorize. Okay, this previous year question was in link with the halogen only. Okay, when it comes to alkenes. Now third reaction is addition of water, that is hydration. So alkene plus water in the presence of hydrogen ions and mercuric ions gives rise to alcohol according to the Markovnikov addition. Example can is given here. Now comes the oxidation. There are two methods of oxidation. One is called as Bayer's test, in which cold dilute potassium manganate is used. You can see that in order to produce the conversion of purple into brown and glycol. Strong oxidizing agents can also be used apart from the general Bayer's test, that is the oxidation reactions of alkenes used to locate the position of double bond. Ozonolysis, very high yield for NEET. What is happening here is this alkene is getting into reaction with the ozone, that gives rise to our ozonide. It is an intermediate. Then in the presence of zinc and water, it gives rise to carbonyl compounds, that is aldehydes or ketones. This is very important for NEET examination. There was a previous year question. You have to stop this video and study the previous year questions. Another type of chemical reaction is polymerization. Here what happens is ethene is converted to polyethene, propene is converted to polypropene. The key points are alkenes undergo electrophilic addition reactions easily. Markovnikov's rule is general, peroxide effect is only for HBr. The bromide and potassium manganate test for unsaturation. Ozonolysis very important for the structure determination. Alkenes polymerize to form useful polymers. I would like you to subscribe to the YouTube channel, like the video and comment in the comment section what do you have any doubts or do you want any other topic for me to teach, and do share with your friends. Stability of alkenes. So there are general principles. Okay, more substituted alkene is more stable due to positive inductive effect and hyperconjugation. So if there are more substitutes, then that alkene is more stable. Hyperconjugation you can see in the diagram. The order of stability is ethene less than mono substituted, less than di substituted, it means more substituted, and less than tri substituted, and less than tetra substituted. So therefore more is the substitution, more will be the order of stability. Geometrical cis-trans isomerism. So geometrical isomerism, obviously you can see in the arrangement, the 3D geometrical arrangement, the trans isomer is more stable when compared to the cis isomer in alkenes. In the trans isomer, groups on the opposite side are present and less steric hindrance can be seen, therefore it is more stable, whereas the cis isomer is less stable, and the groups are on the same side and more steric hindrance, therefore it is less stable. So stability order trans is more than the cis type of geometrical isomerism. The reason is substituent groups, alkyl groups, donate electron density to the pi bond through hyperconjugation. Sigma single bond CH gives rise to pi carbon double bond carbon. More the number of alkyl substituents, greater is the stability. Trans isomer has less steric repulsion than the cis isomer. Why the trans has less steric repulsion? Because it has having less steric hindrance. You have to remember that one. Useful relation, enthalpy of hydrogenation, okay, is inversely related to stability. More stable alkane, lower enthalpy of hydrogenation. Less stable alkene has a higher enthalpy of hydrogenation. You have to note one thing, that catalytic hydrogenation adds hydrogen across the C double bond C bond to form the alkane. You can see there are two previous year questions. Stop the video and study those two previous year questions thoroughly. Alkynes, CnH2n minus 2. Alkynes, CnH2n-2. Structure of the triple bond. Carbon in alkyne is sp hybridized. Geometry is linear with bond angle 180 degree. Triple bond consists of one sigma bond and two pi bonds which are mutually perpendicular. Bond length is 120 pm and bond enthalpy is 823 kilojoules per mole. So you can see there are two pi bonds above plane and below plane. One sigma bond is formed by head-on overlap of sp orbitals. Two pi bonds are formed by the sideways overlap of the unhybridized orbitals in perpendicular planes. Hence carbon bond is very strong and shortest. The nomenclature, position isomers and chain isomers. So you can see if the position, according to the position, but-ine, and internal alkyne, it is but-2ine. There are chain isomers also. Acidic character of the terminal alkynes. In the terminal alkynes, the hydrogen is attached to sp hybridized carbon. Sp carbon has 50% S character, more electronegative compared to sp2, that is 33%, and sp3, that is 25%. This makes the CH bond more polar and H plus can be released easily. Hence, terminal alkynes are acidic. So after that one, let's see nomenclature and isomerism. Obviously, this nomenclature, isomerism, position isomerism, and chain isomerism we have studied in the basics also. Acidic character of the terminal alkynes. In terminal alkynes, the hydrogen is attached to sp hybridized carbon. Sp carbon has 50% S character, more electronegative compared to sp2, 33%, and sp3, 25%. This also we have studied in our previous slides also. This makes the CH bond more polar and H plus can be released easily. Hence, terminal alkynes are acidic in nature. So this is the reason behind that one. So there are few PYQ questions also. Please solve these and study the whole slide multiple times. Alkynes, acetylenes, CnH 2n minus 2. So preparation of alkynes from calcium carbide, from vicinal dihalides, from terminal alkynes, alkylation. So these are the methods. Industrial source of ethine is coming from these, basically from calcium carbide. So industrially it is produced from calcium carbide. And addition reactions you can see here: hydrogenation, halogenation, and addition of HX and hydration. So almost when compared to alkenes and alkynes, almost are similar. Okay, polymerization of alkynes, linear polymerization and cyclical trimerization also can be seen in case of alkynes. Stop the video and study the previous year questions. Oxidation of alkynes is very important. Ozonolysis of alkynes gives diketones or carboxylic acids. The general reaction here has been given in the presence of ozone, zinc, and water. It breaks down into an alkyne, breakdowns into diketone and carboxylic acids. Example are pent-2-ine under the presence of ozonic lysis and zinc and water breakdowns into ethanoic acid, acetic acid, and propanoic acid. Key points: ozone adds across the C triple bond C bond to form an ozonide. Ozonide on work of that is reductive action by zinc and water cleaves the triple bond. If a carbon of carbon triple bond carbon has at least one hydrogen, carboxylic acid is formed. If a carbon has no hydrogen, this disubstituted, then ketone is formed. So you can see that in the previous year question also there is a question on ozonolysis. What does it gives? Okay, ozonolysis cleaves the carbon triple bond carbon. If you know that this one, obviously you are going to break it. Terminal carbon having H gives the carboxylic acid, and non-terminal carbon with no H gives ketone. Aromatic hydrocarbons, also called as arenes. The structure of benzene, resonance, and aromaticity. Let's see. These are only direct points according to the examination point of view. Molecular formula of the benzene is C6H6. Planar, it is regular hexagon. All the carbon bond lengths are equal. All bond angles are 120 degree. Each carbon is sp2 hybridized, delocalized pi electrons present above and below the plane. Key features of the benzene, you have to remember all these things. The delocalization of the pi electron, the 6 pi electrons are not confined between two carbons but are delocalized over the entire ring above and below the plane. The Kekulé structures, resonance forms, and resonance hybrid actual structures. What do you mean by Kekulé structures? The Kekulé structures are the structures of the benzene in which we will see the resonance forms. So conditions of aromaticity. First of all, what are the conditions, requirements of the aromaticity that we have to understand? One, the compound has to be cyclic, it has to be planar, it should be completely conjugated at the p orbital on every atom of the ring, and it should obey the Huckel's rule. What is Huckel's rule? We are going to study, but for now Huckel's rule is 4n plus 2 pi electrons. So benzene 6 pi electrons because n is 1, naphthalene 10 pi electrons because n is 2, and what do you call as anthracene 14 pi electrons because n is 3, and phenanthrene 14 pi electrons because n is 3 again, but the bonding is different. Pyridine 6 pi electrons, n is 1. What is Huckel's rule for aromaticity? A cyclic planar completely conjugated system is aromatic if it contains 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3. So non-aromatic means anti-aromatic. Example, 8 pi electrons, 4n system, if planar, anti-aromatic, unstable, actually adopts non-planar tub shape to avoid anti-aromaticity, hence non-aromatic. Previous year questions are very easy to understand and integrate with the topic. The preparation of benzene is by three processes: cyclic polymerization of ethine, decarboxylation of sodium benzoate with soda lime, and from petroleum, that is catalytic reforming. So during the cyclic polymerization of ethine, a red hot iron tube, ethine molecules polymerize on passing through a red hot iron tube at 873 Kelvin temperature, and benzene is formed. During the decarboxylation of sodium benzoate with soda lime. Sodium benzoate on heating with soda lime gives benzene. This is a decarboxylation reaction. From petroleum catalytic reforming, benzene is obtained from petroleum fractions by catalytic reforming. Straight chain hydrocarbons are converted into branched and cyclic hydrocarbons aromatics like benzene. The key reactions of the benzene are 1. Nitration, 2. Halogenation, 3. Sulfonation, 4. Friedel-Crafts alkylation and Friedel-Crafts acylation. So remember, whenever there are named or scientific named reactions, those reactions are very important. These reactions are electrophilic substitution reactions. So in the nitration reaction, obviously the concentrated nitric acid is used and concentrated sulfuric acid is used. Nitrobenzene is formed. In halogenation, chlorobenzene or the bromobenzene is formed. In sulfonation, the benzene sulfonic acid is formed. And in the Friedel-Crafts alkylation, the alkyl benzene is formed and carbocation is seen there. And in the Friedel-Crafts acylation, then acyl benzene, that is ketone, asylum ion, that is the electrophile there. So electrophile and the product formed and the reaction name, that could be the match the following questions also. Stop the video and study the previous year questions. Directive influence, that is ortho para or the meta situation. Ortho para directing groups activating, these groups increase the electron density at ortho and para positions through resonance effect, hence they are activating an ortho para directing. Which are the groups? This OH, OR, NH2, NHR, NR2, CH3, C2H5 and X, there are halogens. The reason is lone pair or positive inductive effect donates the electron density to the ring by resonance or inductive effect. This increases electron density at ortho and para positions, making them more reactive towards electrophiles. So which are the group which can help in the ortho or para directing? Directly a question can come. In the same way, the meta directing. Meta directing means deactivating. These groups decrease electron density at ortho and para positions through R and I effect, that is negative resonance effect and negative inductive effect. Hence they are deactivating and meta directing. The groups are NO2, CN, CHO, COR, COOH and SO3H. The reason behind is these groups withdraw electron density from the ring by resonance, that is negative resonance, and or inductive, that is negative inductive effect. This decreases the electron density at ortho and para positions. Meta position is relatively less deactivated. The illustration of electron density, activating of ortho para directing, deactivating of M directing and halogens, all these can be explained through electron density and on the diagrammatic presentation. The important terms also you have to know. Better stop the video here and study the important terms by heart and also practice the previous year questions. I request all the students to subscribe to my channel and like the video and comment if any topic you haven't understand, or if you are demanding one more topic, so that many students can be benefited with your advice. And I would also like you all to share the video to your friends so that help students. The oxidation and addition reactions of the benzene. It happens through combustion, hydrogenation and addition of chlorine. Let's see. During the combustion in the presence of a sooty flame, then the 15 by 2 of the oxygen burning gives rise to 6CO2 plus 3H2O and has a sooty flame. Hydrogenation to cyclohexane under nitrogen, nickel and under pressure, high pressure, it gives cyclohexane. Addition of chlorine, it gives the gammaxane. Okay, previous year questions are given here. Try to solve all the questions. Benzene resists addition reactions under ordinary conditions due to aromatic stability. It undergo addition only under drastic conditions like UV, high pressure and high temperature. In combustion, benzene turns with a sooty luminous flame due to high carbon content. Distinguishing tests and reagents. The quick summary for alkene and alkyne, and for the distinguishing reaction is bromine in the carbon tetrachloride, and the observation is reddish brown color decolorizes. So presence of carbon triple bond carbon or carbon triple bond carbon unsaturation, no decolorization, therefore saturated alkane. Terminal alkyne versus internal alkyne, it needs ammonical silver nitrate. For primary, secondary and tertiary alcohols, Lucas reagent. Aldehyde versus ketone, Tollens reagent. Phenol versus alcohol, neutral ferric chloride solution, alkanes, alkenes, and alkynes. Such type of distinguishing happens through Bayer's reagent. So you should know what are the reagent which are going to distinguish between what type of compounds. That only table will be enough to answer all the questions. The aromaticity check. A compound is aromatic if it is cyclic, planar, completely conjugated, and obeys the Huckel's rule, that is 4n plus 2 pi electrons. So benzene, naphthalene, pyridine, these all examples show that they are aromatic in nature. Examples of non-aromatic are cyclobutadiene, cyclooctatetrene, and cyclopentadienyl cation. Aromatic compounds have extra stability due to delocalization of pi electrons. You can also see the Markovnikov ionic mechanism and anti-Markovnikov free radical chain rules also. Okay, we have studied already about the Markovnikov addition and anti-Markovnikov in the previous slide. This is just a revision. These are all the formulas that you require when it comes to the organic chemistry and hydrocarbons: ozonolysis, reverse engineering, hydrogenation, enthalpy, order. You should remember all these ordered, all these numbers. Direct fact-based questions are coming from this one. And the enthalpy is more at minus 136, more than minus 124, minus 15, and more than minus 109, and more than minus 95. All these has to be by hearted properly. I again request you all for to subscribe to my channel, like my video, and also comment whatever you have any queries and all those things. And thank you very much. Let's meet in the next video. Stay tuned, subscribe to the channel.